An analog representation of a quantity is proportional to the value. An example of this is a gauge measuring the height of water in a tank. A float device and an indicator are connected to either side of a pole on a pivot, and the level is measured depending on the height of the float in the water tank. As the float goes lower, the indicator goes higher. It covers a range of readings measured on a scale. The deflection of the needle depends on the length of the pole either side of the pivot. Another representation of the height of the water might be by the angle that is made at the pivot, but in this case the angle would not represent the proportional drop in water level because the angle would change less as the level drops more. The speedometer of a car displays the speed by pointing towards a curved scale of numbers where the angle is proportional to the speed of the car. The speed of the car might be represented by current produced by the rotating action of a cable input to the speedometer. Numbers are symbols which can be presented on scales to describe analog quantities. A digital representation uses symbols known as digits, the most common being the base 10 or decimal number system. There are other sorts of number systems known as bases. The base 2 number system is called binary, and only the symbols 1 and 0 are required to represent numbers. The simplest digital system is an on-off switch, where the number 1 can represent the switch in the on position, and the number 0 is represented by the switch in the off position. The base 3 number system uses the symbols 0, 1 and 2. Base 5 makes use of all symbols between 0 to 4. Base 16 will use all the numbers from 0 to 9 but adds 6 extra symbols, A, B, C, D, E and F, to allow for the total number of 16 symbols required to represent a number in that base. 0 is represented in the same way in each of the number systems. In the base 10 number system, after counting 9, the next count adds another column for the representation of the number 10. The 0 symbol is the original symbol, and a 1 has been placed in the column to the left. In base 2, the count starts from 0. The symbol 1 comes next, and given that there are only 2 symbols in base 2, a 1 is placed in a column to the left, and the lowest value symbol, a 0, is recorded in the original column. Each of the original numbers have more than one column with the equivalent of the symbol 0 in these columns, but zeros are not normally displayed in the columns to economically communicate those numbers. In binary, the pattern is 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1. The pattern 0, 1, 0, 1 appears as each number is counted in the original column and will continue like this. A transition from 0 to 1 and from 1 to 0 is known as toggling. In the case of base 10, the count is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then it starts over again. 0, 1, 2. In the case of base 3, it would be 0, 1, 2, 0, 1, 2. As soon as 2 is achieved in the base 3 number system, the next column is incremented. The base number systems correspond with each other. It may be that because humans count by using 10 fingers, that the base 10 number system is most commonly used. If counting occurred using other parts of the body, a different base number system might be used. If, for instance, the space in between fingers were counted, a base 8 number system might be more prominent. The count would be 1, 2, 3, 4 on the first hand and 5, 6, 7, 8 on the other hand. Of course, the symbol 8 does not occur in the base 8 number system, also known as octal. Remember, the base 10 number system makes use of another column at the same time that the final number is counted. The difference between this and other number systems are the symbols which are skipped or added in the representations of numbers. An 8 in the octal system is represented as 1, 0. The ninth number counted will be 1, 1 in the base 8 number system, then symbols in the columns for 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 2, 0. The symbols 8 and 9 are not used in the counting process. Even though a number is represented by the symbols 1 and 0, because it is represented by the base 8 number system, the meaning is 8 in the base 10 system. When counting in the octal system, the first 7 symbols are exactly the same as the decimal number system, but the symbol 8 is not used, so the next column is incremented, and 1, 0 is the next number, as octal numbers are represented. Base 4 would be 0, 1, 2, 3, increment next column, 0, 1, 2, 3, increment the next column. As soon as this column requires the next increment from 3, an additional column is required to represent the next number. So in this case, the next column is incremented, and each of the 3's is changed to a 0. The symbol 1, 0, 0 is attained by counting more quickly in base 4 than with the base 10 number system. 1, 0, 0 in base 4 means the number 16 in decimal, but it is displayed using 3 columns. In binary, the original column toggles as the increase continues, whereas in base 4 the pattern is 0, 1, 2, 3, 0, 1, 2, 3. In this case, the extra columns pattern is 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3, which will then continue with 0, 0, 0, 0, although these weren't displayed during the first 4 representations as leading zeros. The next column will increase every 16 times. In the base 2 number system, that particular column changes every 4th time. At what rate is it expected that each subsequent column will change? The next column is going to change every 8th time, the next every 16th, and so on. Each subsequent column will change with twice as many numbers at half the rate of the previous column. A way to represent the columns is by calling the original column the 0th column, because this represents the power of the base to which each symbol is weighted. Then the next column over would be the first column, the next column over would be the second column, etc. 2 of the power of a particular column number is equal to the effective weighting of that column. 2 to the power of 0 is equal to 1, the minimum counting increment. 2 to the power of 1 is equal to 2, which designates each time that column changes. 2 to the power of 2 is 4, 2 to the power of 3 is 8, 2 to the power of 4 is 16. Interestingly enough, if there is a 1 in any of these columns, we can multiply by the power of 2 to that column, and we will get the result in decimal by adding the number obtained from each of the filled columns. Every number system can be manipulated in a similar way to achieve equivalent decimal representations of that number.